this video, we'll be solving this problem of finding square root of a number. We will be solving two variants of this problem. First one is finding the floor value of square root. So this is the variation which you will see often on programming websites, where you need to find the floor value of the square root. For example, square root of 3 is 1.73 and you need to print the floor value, so 1 in this case. And then we will discuss the second variant, where you just have to find the square root. You don't have to find the floor value, just the square root, and your answer should be correct with the maximum absolute error of 10 raised to minus 6. So if your answer is off by 10 raised to minus 6 or less than that, it will work. Let's begin with the first part. Here we'll be finding the floor value of the square root. Now in this form you will see this question on various platforms like LeetCode, where you need to find the floor value. So let's discuss it first. Here I have taken the number 12. I have taken a smaller number so that it is easier to plot on a number line. Now for those who don't know what a floor value is just the integer value which is closest to it. It is the smallest integer value which is closest to that number. For example, 12.34, its floor value will be 12. For any integer, floor value is equal to that number itself. So floor value for 12 will be 12 only. Here we need to find the square root of number 12. For easy visualization, I've drawn a number line here, and these are the numbers from 1 to 12. Since we are taking the floor value, the answer can only be an integer. And it's really obvious that the answer, that is the square root, will always, square root for any number n will always be greater than or equal to 1 and less than or equal to that number itself. Equal here because for 1 square root is 1 only. So the range will always be in this. Square root will always be in this range. Since we have a range for our answer here, we can first of all try linear search. Maybe find the value of 1 square, compare it with 12, which is less than 12, so we will move forward. 2 square is 4, again less than 12, we will move forward. 3 square is 9, less than 12, we check it for 4 now. 4 square is 16. Now since 16 is greater than 12 and we are looking for floor value, we will take the number before 4. So answer will be 3 in this case. And you can also verify square root of 12 is 3 point something. So floor value will be 3 only. So in linear search, the logic is simple. The first number where the square value will be greater than that number, in this case 12, the previous integer will be our answer. So 3 will be our answer. This was simple linear search. Now since the possible value of answers that we have, it is in sorted form. It's from 1 to 12 only. So why shouldn't we take the advantage of this and apply binary search here? That will reduce our complexity to log n. Whereas in linear search, it was big of n, right? So let's start with the simple binary search. The procedure will be standard. We don't have to do anything different. I will therefore quickly paste the code here so that you can see what we are doing here. We are initializing the left side as 1. So this is the left side, and right side as the number that we need to find the square root for. So these are L and R, and now we have to apply binary search in this head, and at the end we will have our answer. So while this L is less than or equal to right, we will continue with this procedure. First of all, we will calculate the mid value. Mid in this case will be 1 plus 12, and since we are doing floor division, we will have 13.6 as the mid value. So this is the first index that we have to see. Now for easy visualization, you can print the mid value as well, so that at the end you know what all values you searched for. Then we will calculate the square of 6, which will be 36. So it will be 36, and we will see whether this 36 is equal to 12 or not. Because if it is equal, we will straight away have our answer. In this case, it is not, so we will check the next condition. We will compare whether 36 is less than n. It is obviously false because 36 is greater than 12. So we will move towards the else part. Then we will make the mid as mid minus 1. So our next mid will be, right side will be mid minus 1. We can delete this here. And we can discard this complete right hand side. Now we will continue with the procedure here. 1 plus 5, our next mid value will be 1 plus 5. Taking the floor division, it will give us 3. We will again calculate the square value of 3. It will be 9 this time. This is our mid. This 9 value we will see whether it is equal to 12. It is not. We will check this condition, and this time it is true. Since 9 is less than 12, we will make answer equal to mid. So answer now equal to, it is now equal to 3. We will make the left side as mid plus 1. So this is our left side now, and I will delete this part. So this is our left value and this is our right value. Again, the procedure will be same. So I will just quickly move forward. Now square value is equal to 16. We will see if it is equal or not. It isn't. We will check this condition. It will fail, and then we will make right equal to mid minus 1. So right will be updated here and it will be mid minus 1. So right will become this value 3. Now we will check this condition, and since it is false, we will break out of the loop. And our last value of the answer, it was allotted answer was 3. So this will be our final answer. Why are we updating value of answer only when, if it is equal, then it's obvious why we are making answer equal to mid. But why we are updating answer here and not here? The reason for that is we are looking for floor value. Now floor value of the square root, if we take the square of that, that can always be less than n. For instance, here our answer was 3.4 something because square root of 12 is 3.4 approximately. So it was lying somewhere here and we were taking the floor value. So answer was 3. And if we take the square of 3, it will always be less than the n. It cannot be greater than n. That's why we are updating value of answer only when the square is less than n. Now let's move on to the second part. In this part we need to calculate the value of square root, and that value can be a real number. Earlier we were taking the floor value, so answer was always an integer. Now let's see what changes we have to make so that we can calculate this value. It is also given that the maximum permissible absolute error is 10 raised to minus 6. And why that condition is given, let's see. Because now we'll be dealing with floats, and floats are not so accurate. So they might be the case where answer is 2, and since it is a float, your answer comes out to be 2.0001. Even though you have done everything correct, you can get these type of values. Therefore, this type of relaxation will be given to you whenever we are dealing with floats. So just like the previous code, there are few changes here. Rest everything is same. Again, we are applying binary search. Our limit is from 1 to 12 since we are finding the square root of 12. We are initializing square and mid. These are two values which we'll be using later on. So let's initialize it to 0. Then left, we're assigning it 1. Right side, n, which is 12 in this case. Here, instead of comparing left and right, also for the reference, I will just paste the previous code here so that you can compare at what places there is a difference. So instead of left less than right, we are using absolute value between n and square. And the reason for doing this is floats, as I mentioned earlier, are inaccurate. So you cannot directly compare them here because let's say your left becomes 2 and your value of right is 2 point, let's say 0 0 0. After all the calculation, value of right is 2.000 and then there is a 1. Even though you will continue with this process again and again, you might end up with the same value of right. So if you are using this condition, then right will always be greater than left and you will go into an infinite loop because the inaccuracy of floats. So to avoid this thing, we need to take the absolute values here. And if the difference between the absolute value is greater than this number, then only we will continue with the loop. Another important thing to note is this 10 raised to minus 6 value, it is just an estimate and it is not because of this value given to us in the question. This value given to us is for the answer. Let's say if our answer was 2, then we could have printed any number in the range of 2 plus minus 10 raised to minus 6. Whereas this 10 raised to minus 6 is for the difference between n and square. Square is the square of mid value and n is the number given to us. So it is for this difference between n and square. I won't go into much detail of how to calculate the most efficient value for 10 raised to minus 6 here because it will require a little bit knowledge of error analysis, which is completely off topic. So if you're curious, you can figure it out yourself, but in this way case 10 raised to minus 6 works just fine. Moving on, we will then calculate the value of mid, which will be 1 plus 12 divided by 2, that is 6.5, and it will lie somewhere here on the number line. Then we will take the square of this value, it will be close to 42. We will compare it with n, this condition will be false. Then we will enter this condition, square is not less than n. So we will move on to the else part here and assign right equal to mid. So right will be 6.5 now. From here we will move to the top of this while loop and we'll take the absolute value of 12 minus 42, which is definitely greater than this 10 raised to minus 6 here. Again we will be calculating the mid value this time. The mid will be 1 plus 6.5 divided by 2, which is equal to 3.75. So this is a new mid value. Again we will have to calculate the square. This time it will be square of 3.75 is approximately 14.06 approximately. So this will be the square value and we can compare these conditions and we will enter this else part here. You can verify it once for yourself. This means the new value of mid right will be mid. So after updating, 3.75 will lie somewhere here, and this will be a new value for right. We'll delete this previous value. Again, the same procedure will carry on with the updated values. These are all the values that mid will be taking. First of all, it was 6.5, then it decreases, and the final value of mid is this 3.4641, this last value on this slide. One side exercise for you is to figure out what is the time complexity in this case. Is it still log n or is it something different? And if you like this video, do hit the subscribe button, and I will see you in the next one.